There's something new here, pulse iteration, but I'm not going to go into too much detail about value iteration because there's nothing new. We've seen it in the deterministic setting, and there's nothing, and we've seen one version of the stochastic setting. There's not much more to say in a sense. But let me go through and walk through this in a different sort of light. So we've got so just for preciseness, I'm sticking to the average cost optimality equation. And I should say, actually, I just uploaded the homework, and there I am asking you to look at the discounted case. And we're not covering lecture, but as I said, they're all the same. So, you know, it's in terms of the algorithm, you can look it up or ask me. It's very much the same thing. But it's also covered in the book. But let's stick to the average cost optimality equation here. Let's just think about how you might have solved this in a high school or undergraduate calculus course, how you might have thought about this. So first of all, let's make this restriction. Remember, I can add a constant to both sides. 8 star is not unique. So assume let's just take, I'll put a bullet there. I hate the fact they used stars before. It's like, it sounds like X is optimal in some sense, but that's what I used in the notes. But let's, you know, it's got some special state, and I've normalized 8 star to make its value equal to 8 star at that point. And the reason for doing that is that initially I've got 2 unknowns here. I've got 8 star is an unknown and H is an unknown. By doing this, I reduce one unknown. And I get a fixed point equation. So let's unravel this. I'm saying that I can write down a fixed point equation in the form 8 star equals t of 8 star, where t is a functional. It maps functions to functions. Okay, and what is it that's sitting right there? It maps functions to functions. So t of 8 star is a function, and if I evaluate it at x, it's just equal to that, but minus this term here. And forget the stars. For any old function, so I've defined for any function h, t of h is a new function defined in this way. And the average cost optimality equation then is a fixed point equation. And I'm just hoping that all of you have seen how you solve fixed point equations. Yeah. There's 2 ways that I know of. What? I heard it. What? Evaluation. Yeah, well, there's successive approximation is what people normally call it, but you said, evaluation. Well, I mean, I don't know. I'm not sure I understood. Maybe you have a third approach. No, is that what you? Okay. Well, number 1, the most common approach is successive approximation. one is, yeah, successive approximation. And the second, no? Well, how about the zero of a function? So if I write this as t of h minus h, I'm trying to find the zero of a function. How do you find the zero? What?
Root finding.
Yeah. What's the way to find roots?
Like Newton-Raphson.
Yeah. Okay, so those are the two approaches to solve fixed point equations that find roots, and that's that's value iteration, and that's policy iteration. Those are the two algorithms. So there are two algorithms here, and they correspond to these two approaches. So this is something that might have come before. This is something new. Now you can imagine this could scare you. Because Newton-Raphson involves derivatives and all that. I'll review that. And this looks pretty funky in terms of differentiating. But this is for each u, I mean, it's a matrix times a vector. It's a linear equation. And if you take the minimum of linear functions, you get something concave. So t is a really nice operator. It's a concave functional. Okay. Remember, I'm thinking of h as a vector. A finite state space h is just a vector. And we've got a minimum of linear functions. So it's not as bad as it looks. All right. So let's look at this. So successive approximation is just take your new approximation of the solution, and I'll put it up here. When we're trying to get algorithms to solve this equation, I'll just take as your new guess t of the old guess, and you can hope that, well, if t is continuous, if h converges, hn converges to 8 star, then hn plus 1 goes to 8 star, and you solve the equation. So this is just cross your fingers and hope. And if we go and look at this, what does it give us? It says that hn plus 1 of x is th n of x. And it's right there. And that looks very much like value iteration, because we've seen value iteration in a million different contexts, and that's it. Value iteration is exactly the same thing without the normalization. The only difference between successive approximation and value iteration is that in successive approximation you keep on subtracting, normalizing, 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 normalizing. Adding a constant to a function, it shifts the whole function. It doesn't change anything. So you can check really easily yourselves that if you take hn of, h0 equals v0, that'll imply, well, the constants do make a difference, but you can subtract them all. So if I look at the normalized function, Vn of x minus Vn of x bullet, it's the same as the normalized Hn. So, because you just subtract a constant. I'll let you prove that by induction. It's just the fact right here. If I had a constant in this function, I can just pull it out somewhere. So that's that. Now, it will be fun to talk about Newton-Raphson. I'm going to remind you what it is, and then we'll come back to it next time. Okay. Let's see what we have here. Yeah. Now, the minimum of linear functions is concave. The concave function is of its argument. I mean, by now you all should nod your head when I say H is a column vector. And if you don't know what concavity of a function is, then just look it up, okay? But T is a concave function of H, all right? And the reason for looking at H minus T of H is that I get a convex function. And we're trying to solve this equation, which means we're trying to find a root of this equation. And I've made this way too smooth. That's okay. So what do you do in Newton-Raphson? Let's see. What do you do? Let's see if I remember this.
Take the gradient and
Yeah. So if somebody says, hey, I've got a good guess, I think 8 star is here. What you do is you go up there and you look at this point here and you say, it's not that good. I wanted 0, right? Because I want h minus t of h to be 0. So I want to solve that fixed point equation. So what you do is you go through and you linearize. And you can see how well it works. That's supposed to be a straight line. I'm sorry, my hand's shaking, but that's a linearization. And you find the root of the linearization. And there it is. And man, can't you see how it's converging? I mean, but seriously, if you go up here and you look at the next iteration, I couldn't even draw it. So it's awesome. But the only trouble is linearization. So let's see what this means. So this is what T is. Let's forget that for a moment. What you're really doing is saying, basically we're doing this linearization. T of h is T of hn plus some matrix. I'm just going to call it A, so I don't have to, deal with these gradient terms. But it's the gradient of t. So if we're in a finite state space of size n, then H, yes, it's a mapping from a real value mapping on the state space, but it's also an n-dimensional vector. It's H is represented as H of x1 dot 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 H of xn. When I say functions and column vectors, that's what I mean. And so A is going to be an n by n matrix. All right, and so, and then what you do is you Newton-Raphson. So equivalent to this diagram is to replace T by its linearization. So pretend this is reality. So what would it be? So I would love to solve hn plus 1 equals t of hn plus 1. That would be a really great algorithm. I could implement it. I can't because t is so complex, so I replace it by linearization. So that's exactly the same as this graphical interpretation here. I'm just not bothered to look at h minus th. I'm just directly doing the approximation. And so you can shuffle things around and you get that I minus a. There it is. And if you're lucky, this matrix is invertible, I minus a, and you get this nice equation. Now, okay, we'll talk about it next time. So we've got 3 algorithms going. Okay, so I'll explain what this is later on. We have 3 algorithms. Define the linear program for you. You can type linprog in MATLAB. Value iteration, we've written down. It's 3 lines of code. Policy iteration, we haven't seen what it means yet. Nobody on earth in this room could interpret this monster. And so I'll explain what it means on Wednesday. In terms of computation, everyone favors this. At least that's been historically true. The value iteration is considered the only approach for computing policies. That reasoning is flawed because we're never going to compute a policy. Every single problem we look at is too complex to even touch. And so it turns out all these approaches have their benefits. Now, linear programming approach is really easy to approximate. So it's really a valuable tool as well. If you at the very start said, I'm not going to get a very tight approximation, I'm just trying to get the structure. Linear programming approach is a gold. I'll put a question mark there. And when we do see policy iteration, it's going to be useful as well because both, both of these for deal for approximation. So that's the reason for introducing free. So it depends on the setting. Okay. So I'm not going to prove a thing today. I'm just going to tell you what you could expect. So what would you expect? Well, you'd all expect that this solves a finite horizon optimal control problem. So I know it bothered you through the first weeks of the course. I was using V0 here as a terminal cost. But it's the same thing. So V0 is the initialization of successive approximation. And you have to initialize this algorithm. When you initialize it with the function V0, it turns out to be the terminal cost. And this is what you do in model predictive control. But in model predictive control, you get a sequence of policies. I'm sorry, VIA, sorry. When you perform this minimization over all controls, you get a sequence of policies. These are the sequence of policies we've studied before in the deterministic setting. But the definition of MPC is to give up. You take that and stick with it. So that's the definition of MPC. You don't use, when you solve this finite horizon optimal control problem, you get a sequence of policies, but you just use the first one. And that's not often the way it's presented. That's really what you're doing. Okay. And so what else? Let's just summarize what we know. We know that if we can guess. If, as before, as in the deterministic case, suppose that V V0 is the Lyapunov function for some policy. And what does that mean? It means that, in the sense that we talked about before, that let's look at a name. It's called phi. So what do I mean by this? I mean that if somebody gives me a stationary policy, I get the resulting controlled process is a Markov chain, and P sub phi just denotes its transition matrix. Okay, that's the notation here. So when I write C sub phi of x, with a given stationary policy, I get a transition matrix now, which is fixed. It's just a Markov chain. And I've got a cost function just on the state space because I'm always applying the control U equals phi of x. And so this is a Poisson inequality. And so remember the deterministic setting, we said that if this inequality held for the first policy, it'll hold for all subsequent policies.